Hello, good morning. So, good evening. We will start the discussion in 5 minutes. Let's get remaining people also join. I think we can start now. I think you have all gone through the NPTEL course of first week, welding metallurgy. It is today we will try to discuss what, in summary, what is the course content of this welding metallurgy for the first week. That is what is introduction to what is the welding, and what is the different type of weldings, and how the metal properties affect because of the welding process, and what is the different kind of phase diagrams for ferrous materials and non-ferrous materials, and yeah, those concepts. I think those are the mostly concepts which will be covered in the week one. That will be summarized for a certain time. Then after we will try to solve the few questions from this one, so that you can do your assignment of this course much better. Okay. I think so. So what is the welding process? We can say that in generally manufacturing means we take a raw material, we convert them into useful product. That process is called as a manufacturing process. Okay. In manufacturing process we can classify them into two ways in terms of mass conversion. So if I take the raw material of 1 kg, my final product is also 1 kg, then there is no change in the mass. So we can, for example, casting, forming, forging. In that case, if I take the what are the raw material I am taking, final product is also same mass. In case of machining, if I take a 1 kg of raw material, I will remove the material from it and to achieve the my desired shape. So I am reducing the mass of the component. So I am so final component has the less mass compared to the initial component. So this will comes under the second category, mass reduction. In third category, we are adding the mass. Okay, such as joining in the, that is welding also comes under this mass addition category. So in this case, if I take a 1 kg of raw material, at the final product I will have a more than 1 kg because I'm using a filler wire to join the two materials to get the final component. So so welding comes under the this category. Okay, so these are the mass conversion categories which we have discussed. In case of casting forging, there is no change in the mass. What are the raw material we are taking, that will be the final one. So in case of cutting, machining, we remove the material to get the final product. In case of welding, we are adding the material uh, to join them and to get into the desired shape. Okay. So in joinings, we can classify them into three ways. Okay, well, like one is the temporary join, next is the permanent join, and semi-permanent joint. Okay, so temporary joints are nothing but we as many times I can both two of the components detach them and attach them as many times I want. Okay. Example, nut and bolt. Those are I can remove it and join it as many times I want. Okay. In case of semi-permanent joints, I will use the it is a, we cannot say like totally permanent joint cannot we cannot continuously take it out and join it. Okay. Example, riveting. Riveting is considered as a semi-permanent joint. In case of welding, in case of permanent joints, welding, brazing, soldering, these are all comes under the permanent joints because we are melting the material and joining them. Without breaking that component, we cannot separate both of them. So that's why it is called as a permanent joints. Okay, welding comes under the permanent joint. So how the welding we can define? Okay, so everything going fine, right? From your side, you can listen and going fine now. Okay, we will proceed. So how we can define a welding? Okay, welding is joining of the two materials. Okay, by using heat or pressure. Okay, we are joining two materials by using either heat or pressure to make it as a permanent joint. Okay, in ideal case, so if I have a two surfaces perfectly atomic level is smooth, and if I bring them together because of atomic interaction, those will become joined by themselves. Okay, but in nature we never get a perfectly smooth surface or perfectly without any contamination. So that's why we give the heat input so that the material, the region will become melt, and melting nothing but a its randomness, entropy, its energy state is increasing, so those will become atomic vibrations increases and it will become joined together. I mean, it will mix atomic levelly and join together. Okay, So as we said, welding definition, we can join them by using the heat or pressure. Okay, so if based on that, we can classify the joining welding into two processes. Okay, one is the fusion based welding process and solid state welding process. Okay, what do you mean with fusion is that we are using the heat to join the two materials. It is called as a fusion based welding processes. Okay, in case of solid state welding, we are not using any heat, but we are using the pressure to join the two materials. Okay, these are the broader classification in terms of welding. So these are the sub classifications in fusion and solid state welding. So in case of fusion welding, there are fusion means we need heat to melt them and join them. So here we can produce the heat by different processes. Okay, first one is the arc welding. In this case, we get the heat by uh, uh, electric arc. Okay, so here generally in arc welding we are having a one electrode and base material. Okay, the electrode will be connected to the one portion of the power supply, either positive or negative, and other portion will be connected to the base material. So that if I bring the electrode near to the base material, so the gap between the electrode and base material is sufficient, then the arc will generate. That arc will produce a thousands of degrees of heat. That heat we will use to join the two materials. Okay, it is nothing but similar to if we took it two electric wires which are electric current is passing through, I mean positive and negative, and bring them together, you can see some kind of sparks. Similar kind of principle we are using in case of arc welding. In case of gas welding, we are using a chemical reaction to generate the heat. Okay, like we will use the oxygen and chemical fuel like C2H2, C4H4. Those we will use to, and both of them we will mix, and uh, the fusion will take place. That I mean combustion will take place. That will generate the flame. That flame temperature we will use to join the materials. Next one is the resistance welding. Okay, resistance welding, here heat will be generated by uh, friction and resistance process. Okay, so first one is the resistance spot welding. Example one of them is the resistance plus welding, friction welding. So here because of the material resistance property, in case of resistance spot welding, we have a two electrodes similar to the arc welding, but in this case the two electrodes are connected with placing of the our seats workpiece between the two electrodes. Okay, so once the current is passing through one electrode to other electrode through this workpiece, the because of the material property of resistance, every material have a certain resistance to transfer the electricity through it. So because of this that resistance, heat will be generated. That heat we will use to join the material. In case of friction welding, we use the if two metallic cylinders are there, one is rotating in clockwise direction, other one is rotating in a counterclockwise direction. If I bring both of them together, so because of the friction between those two contacting surfaces, the heat will be generated. That heat is will makes the contact surfaces melt and make it join. Okay, so these are the comes under the resistance welding. Okay, and the fourth one is the high energy welding. Here we use a electron beam welding, laser welding, we use a very high power density uh, light, uh, I mean electromagnetic radiation we will use to melt the materials. Okay. In case of electron beam welding, we use a electron beams as a uh, heat source, and in case of laser welding, we use the laser power source as a heat source. Okay. In similarly, we have a solid state welding. Here, solid state welding means we will use the pressure to join the two materials. Okay. So in case of solid state welding, there are subclassifications are there, like diffusion welding. So it is we bring the two contacting surfaces at very high uh, surface finish is very near atomic level, nanoscale level, and we bring them together, and we raise the temperature of those and we apply the pressure, and we raise the temperature below the recrystallization temperature. Okay. So then the material start, because of the atomic vibration, and the material start getting bonded together. Okay. Similarly, rolling welding, we take the two sheets, two metal plates, and we make it roll and so on. So the because of the pressure, the contacts, the both will become joined. Okay. Friction welding and forge welding, those are also similar cold working processes. Okay. These are the broader classifications of the welding processes, you can see. And other sub classification also there, such as thermite welding. Here, uh, thermite welding mostly used to join the railway tracks. Okay. So how it works is that it is mostly works with the principle of chemical reaction. Okay. Wherever we want to join, we so here you can see how the thermite welding will looks like. Here, this is the thermite welding. So wherever we want to join, there we uh, in that region we add the desired proportion of the two chemicals. Exothermic reaction will take place. The exothermic reaction will generate lot of heat. That heat we will use to that we will melt the material, and that melted material will pour into the this cavity to get the welding joint to take place. Okay. This is the friction welding. You can see two counter bodies rotating in the opposite direction. So because of the contact surface, high heat will be generated. That heat we will use to join the those two materials. Okay. So till now, the classifications of the weldings clear. I mean, okay. Okay. So let's proceed. So we have seen the different.
So,
Yes,
hello.
yes, yeah, yeah, yes, please.
In the
Yeah,
classification, there is in the gas welding there is pressure gas welding. What is that actually?
gas welding. There is a pressure gas welding. This is the gas welding. Okay,
Down.
here you are
Second,
talking about
second classification. Yes, this one.
this one.
No,
Okay.
no, this one. Next slide. Next slide. In the gas welding, see, last is pressure gas.
Okay, okay.
Which like what kind of pressure gas it is?
I have to look into it. I am not sure, but yeah, next class I will see.
Okay, okay.
Yeah, sure. Yeah. Let's proceed further. So we have seen the different classifications in the fusion welding processes. Okay, like oxy fuel gas, I mean gas welding, arc welding, resistance welding, and energy beam welding. So each process will offer a different kind of power density. Power density means per a unit area how much amount of the energy we are giving it. Okay. So in case of fuel, oxy fuel at max it will generate the temperature of 3000 degrees, 3600 or like that. We will discuss briefly into the what is the different kind of this kind of gas weldings. But in generally we will get the maximum of 3000 degrees or like that. Okay. Where is it? Yeah. So because of that, the power density per unit area will be less for unit volume. Okay. But in case of arc welding, it will be around 50 watts. In case of resistance welding, it will be 1000, and laser beam and electron beam welding, it will be 9000 and 10,000 watts per mm square. Okay. For unit area, we are giving the more energy. How it will affects the welding process? Uh, that so if power density is less, okay, if I want to melt the material and join them, so so if I want to join the two materials, so these are the two metal blocks, as you, okay. So if I want to use the oxyacetylene, any gas welding process, because of its power density is less, so we have to apply the gas affected region will be very high, because oh, the amount of the heat is distributed per unit area, so we have to apply for a very long area in the both parent materials, so the heat affected zone will be much more higher. So the region where the metallurgical properties changes, it will be much more broader. But in the case of once this power density increases, so in case of laser and electron beam welding, because of high power density, once the laser beam came, because of the high power density, it will immediately started the forming this weld bead in deeper penetration. Okay. So the heat affected zone will be very minimum, very minimum. So when the power density increases, heat affected zone will be very smaller. But when the power density is low, the heat affected zone will be much more broader. So how the heat affected zone will changes its material properties, those things we will see in further case. Okay. So in conclusion of this slide is that whichever the power density is higher, that will be much more preferable for any welding process, because the heat affected zone will be less, and which will do not change the metallurgical properties of the parent material. But problem is that this electron beam welding and laser beam welding are much more expensive, so we cannot use for the, I mean, any general applications. So any specific, very specific applications only we are going for this one. So in generalized applications, we will go with the arc welding and oxy fuel welding and so on. Okay. So this is the weld bit. How it will be looks like, some welding terminology you can say. So what are the materials we are joining? Those we can call it as a parent materials. Okay. And the welding where it is taking place, it is called as a weld zone. Okay. This weld zone includes this welding bead and heat affected zone. Okay. So entire this zone is called as a weld zone. Okay. This is the welding material, orange color one, and which is the portion which is coming below of this parent material. This is called as a root, and this is the I mean, This is the toe and access to weld face and different terminologies. So this slides is completed. This is okay. So this is the similarly what we have discussed. So if fog density is too low, heat may not be enough to completely melt the material. So the melting never occurs. Okay. If fog density is too high, so it will simply evaporates the material. It will there will be no melting will takes place. Okay. If in case that we can encounter in the case of laser welding and so on. So if laser power is too high, the instantly once the material receives that laser uh, energy to thermal energy, that is enough. That power is enough to completely vaporize the surface layers. There is no enough time left to the top layer to transfer that heat to below layers. So immediately vaporizes. So that is also not desirable for the welding. We just want the in between. They so that the material will be melted, the material and it will become solidified after the cooling process. Okay. So this is the broader overview of the different classifications of the welding processes. Okay. So why we need to study the metallurgical perspective in when coming to the welding process. Okay. So this course is about welding metallurgy. So first, what is the different welding, what is the welding, and so on, different welding process and so on. So second is the metallurgy, how it is affecting its why we have to study the metallurgical properties. Okay. So any materials if you take, so famous example is that, so once the metallurgy metals human, I mean, we are started utilizing it. So we started with the bronze age and iron age and so on. So one of the famous this kind of studying the metallurgical properties is that maybe you have listened this Titanic story, that they have made the Titanic ship, even though it hit the iceberg, it will not supposed to be fail. Like that they have designed it, but they have designed it at the room temperature conditions. But when the Titanic ship is hit, it was at the my very low temperature. So at that temperature, because of the metallurgical properties of that iron, it become, instead of ductile material, it is a transition to brittle material. That's why it become got cracked and the Titanic incident was occurred. Okay, in according to their design, it shouldn't get failed. It may get dent, but it may not fail. So the metallurgical properties is very important when we deal with the um, high temperature, this kind of so temperature plays a very crucial role in terms of how the our component behave. Okay. So welding, if I going to make a power any boiler or any thermal power plant component or anything. So if we are dealing with the temperature, we must consider its effect on its metallurgical properties. Okay. So if I'm doing a making a boiler using a welding process, so metallurgical properties shouldn't be changed, negatively affect the its final component. Okay, final boiler component. So if suppose doing welding makes it as a much more less strength or less uh, stress, I mean it generates more stresses, so it may get to break easily. That shouldn't be occur. So that's why we have to consider the metallurgical aspects, how this melting and cooling will affect this final component. Okay. So we can see this one, this image here, right side one. So this is the how the welding affects the metallurgically a given material. Okay. So here is the parent material, this region. There will be no effect on the metallurgical level. But once we come near to the weld zone, we will see the big columnar grain, big grains. Okay, this is we can call it as a heat affected zone. So what does mean by heat affected zone is that here temperatures reaches above the recrystallization temperature of the parent material. Here parent material means this which are the material we are joining. Okay, it reaches the above recrystallization temperature, but not enough temperature is there to make it melt. Okay, so because of it reaches above recrystallization temperature, so the smaller grains will become merged and become a uh, bigger coarser grains. So that's why here microstructure will be bit different from the remaining parent material. Okay, in case of welding bead, we mostly see the this kind of columnar grains. Okay, why the columnar grains we see is that, so columnar grains happens when the cooling occurs very fast. Okay, so in case of welding, suppose if you see the arc welding process, it will reaches the thousands of degrees in a fraction of few seconds, and immediately cool down to 500 degrees or 300, whatever the temperature, in within a upcoming 3 to 4 seconds or like that. So because of the faster heating, faster cooling, the grains will form in a form of columnar grains. Okay, so we can divide in terms of metallurgically three ways, four ways. One is the fusion zone. Okay, this is the nothing but a weld bead. Okay, weld interface and heat affected zone. Weld interface is the here the line between the heat affected zone and the weld bead, and unaffected base material zone. Okay, so one of the most commonly used welding processor, one is the arc welding. Second is the gas welding. In general, general case, general purposes, people which uses. Okay, so in arc welding, based on the how so what is the arc welding principle? I think we have seen, right? Mm. So we have a power supply, and this is the workpiece, and we have a electrode. So here we can connect this power supply, one portion to the workpiece and other portion to the electrode. So between this electric potential between once we bring this electrode near to the workpiece, because of the electric potential, arc will generate. That arc will give the enough heat to make it the workpiece to melt. So there are three possible cases we are having here. Okay, is this negative portion to the workpiece and positive portion to the electrode. This is the called as a, this is the one kind of setup I am having. And in another case, I am connecting this positive portion to the workpiece and negative portion to the electrode. This is also possible. Okay, cases those are belongs to the DC category. In third case, it will be the AC. In case of AC means it will be the 50% negative side. Okay, these three different configurations are possible through the arc welding. Okay, so based on that, we can classify them into three ways. One is the DCEN, that means DC current, electrode, negative. Okay, so here I am connecting electrode to the negative portion and workpiece to the positive portion. So what is the effect in case? What we'll observe is that if I am connecting negative portion to the electrode, so electrons moves from the negative to positive side. Okay, so that the heat generation always in a blunt way is that always more heat generated at the positive side. So here positive side is the workpiece. So most of the heat, one third, two-thirds of the heat will be generated at the workpiece case, and one third of the heat only generated at the electrode case. Okay, so this kind of configuration we will mostly prefer in the case of where we want to join the thick materials. Okay, and we don't want to electrode to be that much to be consumed. Okay, in that case we can go with the DCEN case. Okay, because electrons flow from the negative to positive direction, so positive side will be the more amount of the heat generation will takes place. In case of DCEP, once I connect to the, similarly this is the DCEP configuration. So minus is the workpiece and positive is the electrode. So here electrons flow from the electrode to workpiece to the electrode. Okay, so in this case two-third of the electrode will be uh, heat with two-third of the heat will be generated at the electrode side, and one-third of the heat will be generated at the workpiece side. So what is the advantage where we are going to use this kind of DCEP configuration is that where we want to have a very less depth of penetration, mostly for the thin plates, thin sheets to join them. That time we can use this DCEP configuration. So second thing we can observe is that in DCEN case we have a very deep uh, weld bead, but in and width is smaller. But in case of DCEP, it is the width is higher and depth is the shallow. AC comes in between case. I mean, between the DCEP and DCN, because it is the 50% of time DCEP, 50% of the time it will be DCN. Okay, so and second, what is the advantage I will get with the DCEP case is that, so compared to the electron, if electrons are moving negative to positive side, ions will move from the positive side to negative side. Okay, compared to electrons, ions will have a much more high amount of the mass, much more amount of the weight. Okay, once those ions come and hit the workpiece, it will makes it as a cleaning action. It will bombard the surface and removes the any contamination or any oxidation layer forming. Those we can easily remove it. Okay, so where we are going to require this kind of configuration is that, if suppose if I want to join aluminum case, aluminum can readily form the oxidation. Okay, because uh, aluminum uh, highly reactive to the oxygen and form as a oxide layer on it. So we which is not desirable in the case of welding process. So that's why we uh, go with the DCEP case. So ions, in that case it will be cleaning action will be takes place. Once the oxidation layer immediately forms, it will be removed by this ions. Okay, so here in case of AC case, it will be only off cycle will be the cleaning action takes place. Okay, so because off portion only it will be DCEP and off portion it will be DCEN. Okay, so these three uh, classifications are okay, right? Okay. So, and the second thing what we have to consider is that in DCEN case, because of the less heat is generating to the electrode side, so we can use the electrode much thinner also. It is mostly in the case of TIG case. So in arc welding also there are sub classifications are there. One is the TIG welding. Second is the MIG, SAW, and SMAW. Okay. TIG welding is the tungsten inert gas welding. Okay, in tungsten inert gas welding, the electrode will not get melt because here name itself saying it is that electrode is made up of tungsten, and we are inert gas. We are using a inert gas to uh, provide the shielding environment surrounding the arc. Okay, why we have to provide the shielding environment, that I will tell you just a moment. Okay, so suppose see here, this is comes under the SMAW. Here you can see I have written four classifications here. Where is it? Yeah, four classifications. One is the TIG, tungsten inert gas welding. MAG, metal inert gas welding. SAW, submerged arc welding. Fourth is a SMAW, shielded metal arc welding. Okay, so why we call it as a shielded, and so here in this case it is shielded metal arc welding we generally see at the home or nearby any welding shop. So where the electrode will have a certain kind of coating on it. Okay, which we call it as a flux. Okay, so why we have to provide is that so when we coming to deal with the metals, what we want to avoid the most is the oxidation, because once the in bulk material, if oxide is formed, it will makes it as a material strength drastically reduces, because oxide is a not, it will not form as a crystalline structure, it will makes it as a brittle, and makes it as a weak part. Okay, in any metal component. Okay, so we want to avoid the any case oxidation. Okay, so any given material who which will be easily get oxidized when the temperature is rises. Okay, so if the temperature of the welding is much more in case of welding, once the it reaches thousands of degrees in molten state, it will be readily to form the oxidation with environment. Okay, in case of room temperature, because of the temperature is low, the metal surface may get oxidized a little bit, and it will not that much affect the bulk properties. But at higher temperatures, it will enter the molten pool may become oxidized, and which will degrade our component. So we want to avoid this kind of oxidation. Okay, so that's why we provide this kind of flux. That flux will act, so during the once the arc is generated, this flux will first evaporate and forms as a shielding environment, so that oxidation cannot come and interact with this kind of molten pool, so that though there will be no oxidation. Okay, so one thing in case of arc welding we have to consider is that we must provide a sealing environment, so that molten metal will not get the oxidized. Okay, so in SMAW case, we are providing the flux through this shielding environment is generated. Okay, in case of TIG and MIG cases, we are using a inert gas such as helium, argon. Those gases we are using, so that those gases will act as a shielding environment, the environment around the weld bead, so that it will not make it react with the oxygen. Okay, these two processes. So in case of TIG welding, electrode is non-consumable electrode. So tungsten is the very high melting point is there, so it will not get melt, but we will provide a separate feeding material. I will show you the how the TIG welding looks like. So here is the TIG welding. You can see here. Here is the fixed electrode, and we are supplying the inert gas to the welding arc region, and here is the filler material. Filler material is the one which will melt and forms as a weld bead. Okay, similar to the like what we have discussed, power supply are having one portion is we are connecting to the base material, other portion we are connecting to the electrode, whether it is DCEP, DCAEN, EAC, based on our applications. Only difference is that the way we are providing the filler material and the way we are providing the inert environment, these two are the difference for the case of all these processes. In case of MIG welding, we similarly we are providing the inert gas environment, but here we are not providing any filler material because here electrode is the filler material. It will continuously fed, and once it is arc, it reaches the arc region, it will melt and forms as a weld bead. Okay. In case of SMAW, shielded metal arc welding. So in this case, which we generally see at home, nearby home or somewhere. So here we electrode having the coating. Here we are providing the shielding by this flux, and the electrode itself will be consumed and forms as a weld bead. Okay, this flux is will once it is the heating is done, it forms as a slag because it has a low density. So it will come up on the welding material, and we can remove the slag by just using wire brush or wire brush. Okay, this is the broadly classifications of the arc welding processes. Okay, because the arc welding is the one of the most commonly used welding process in when you consider in any case. Okay, remaining processes are there, but those are very specific applications. Not as a general welding process. Okay, and coming to gas welding, so based on the fuel and oxygen ratio, we can classify this gas welding into three ways. um, so I would like to inform the one thing that this meeting, it here it is showing that it will be call will be ended in 14 minutes. Maybe after that you can join the again link, again this link only, join back again. Okay, because I cannot control this part. Once it is a suddenly got call ended, you can join back again. I will continue this one. So it is totally 2 hour session. So that next hour or last 15 minutes we will do the some problems of this week course. Okay. Okay, let's continue. So gas welding, we similar to the arc welding, we are also having in gas welding three different classifications based on the what is the variabilities we are having. Okay, so in case of gas welding, just to see here, where is it? Where is it? Yeah. Yeah, see, this is the how the gas welding takes place. So we are having the one fuel mixer fuel, whether C2H2 or any ethanol, ethanol. So here is the how the chemical reaction and heat will generate. Okay, so we are having the fuel and we are having the oxygen. Both two we are having in a two different cylinders. Okay, so we can control the amount of the fuel coming into the this mixing chamber, and we can control the amount of the oxygen coming into this mixing chamber. Okay, so once both of them came here, one those will be mixed and generate the heat. Okay, we can think like a gas stove is also one of works on similar principle. Okay, we are having a one gas cylinder in gas stove, which have the fuel and the oxygen. We are taking it from the environment. Okay, so both two will mix and generate the heat because in the gas, I mean home gas stove. Oxygen we are getting it from the environment. So there is lack of oxygen makes it the amount of the heat generated there will be less. Okay, but in case of welding we want the more heat, so that's why we are providing a oxygen as a separate cylinder, so that we will not face that oxygen deficiency during the welding process. Okay, so once both of the fuel and oxygen mixing in this chamber, and once those got ignited, the flame will generate that. So we will provide a filler rod. So that flame, that heat will be makes this filler rod to melt, and the joining will be takes place. Okay, so there are the three classifications are there based on the what is the variabilities are available here. Variabilities are there. So here we can see only one variability is that how what is the ratio I can supply this oxygen to fuel. Okay, this is the only variable we can have. So based on this variable, we have the three different classifications. So one is the carburizing, one is the carburizing flame, neutral flame, and oxidizing flame. Okay, in case of carburizing flame, we are supplying the more fuel and less oxygen. Okay, so because of the more fuel, there is no amount of the oxygen is I mean there is no enough amount of the oxygen is available, so the fuel may not be completely burn out. So we can see it may form as a black fog, I mean black kind of residuals also, which are the leftovers of the fuel unburned components. Okay, and because of the not complete fusion, the heat generated also will be less compared to the remaining two processes. Okay, so in case of neutral flame, so here in neutral flame we are supplying the proper amount of the, I mean uh, exact required amount of the fuel to oxygen ratio. So it is the ideal condition for the most of the welding processes, because there will be no excess oxygen and there will be no excess fuel also. So it will be the complete burn case. And third one is the oxidizing flame. So in this case we are supplying the more amount of the oxygen. Okay, so here what is the problems we can observe is that because of the high amount of the oxygen is available in the flame. So as previously we have discussed, oxygen is the very bad uh, in terms of the metals. Okay, so we don't want oxygen near the molten pool region. Because of this excessive oxygen may can react with the this molten metal and may form as a oxidizing materials. Okay, so but this will give uh, so you can see the my screen, right? Hello, you can see my screen now. Okay, so in case of but oxidizing flame will generate the much more higher temperature compared to the remaining processes, but problem is that it may causes the oxidation in the welding pool. Okay, so which is not desirable. So where we use the oxidizing flame is that where the molten metal is not that much affected by the oxygen. Okay, like copper and copper base alloys. Okay, and neutral flame we can use for any materials. Okay, but this oxidizing flame we cannot use for the any iron materials, because iron is very much highly react with the oxygen at the high temperatures, so we don't want that. But in carbonizing flame where we use that to make the it where we want to do the surface hardening processes, like that. Okay, high carbon steel and so on. So as I said previously, a carbonizing flame there is a forms as a black kind of smoke kind of thing, because not completely the fuel will be burnt out, because there is no enough amount of the oxygen is there. So whatever the leftover is the carbon. So the carbon will react with the molten pool. Once the carbon content in the molten pool increases, the hardness of the material will be increases. Okay, so in that kind of applications we can use this kind of carbonizing flame. So these two are the one of the most common used welding processes which we can use. Okay, so now for this, with this, the introduction to welding process is completed. Let's go further with the um, metallurgical aspects. Okay, Okay, this is the different kind of welding process as we have discussed. Okay, in summary, we can just wrap up the things. Okay, so we have seen what is the welding definition. We have seen the what is the welding terminologies, and power density we have discussed, and what is the different classifications of the welding processes, and how why we have to study the metallurgical aspect when it comes to the welding, and how the power density affects its heat affected zone and weld zone and so on, and different classifications of the welding processes like fusion welding and solid state welding. Okay, and we have seen the different welding processes. In arc welding we have seen what is the sub classifications in the arc welding, how we classify them in terms of current types, and what is the different TIG welding, MIG welding, SMW, SAW. SAW means submerged arc welding. In this case, arc will be totally covered with the flux material. So here here power efficiency is much more higher because there is no heat loss. I mean, there is a compared to the remaining TIG, MIG, SMW, we can get a very proper deep penetration and proper beat. Okay, and we also see the different kind of gas welding processes. Okay, so next coming to the metallurgical aspect. Okay, so one of the most so first thing we have to see when coming to the metallurgical aspect is that first is the iron carbon diagram. Okay, so iron carbon diagram, here we can see here in a x-axis it represents the amount of the carbon percentage in the iron. Okay, and y-axis is the temperature. Okay, so how with the cool so there are the different kind of phases forms where when the temperature is changes. Okay, those we can see from here. So once the a liquid during the solidification time forms as a two different kind of phases like alpha plus alpha and beta. Mm. It called as a eutectic reaction. Eutectide is that one phase will convert into the two different kind of phases like beta and gamma. This is called as a eutectide phase, eutectide reaction. Okay, and periodic reaction when a liquid plus a solid phase converting into a other solid phase. That is called as a periodic reaction. Okay, peritectoid is the two different solid phases.
Sir,
No.
your voice is not coming.
Oh, sorry. Hello, can you listen? Oh, I think it's hello. Can you listen? No.
Yes, yes, now we can hear.
Yeah. Yes. Yes. So peritectoid, we are having a two solid phase. Once the temperature is reducing, it will form as a another solid phase. Okay, and monotonic reaction when the one liquid and converting into the one liquid plus solid phase, and monotectoid is that one solid converting into two different kind of solids, and synectic is that two liquids forming as a one solid phase. Okay, so this kind of reactions we can clearly see, we can try to observe in the iron phase diagram. So here if you see here one liquid converting into the liquid, one solid phase plus liquid phase when it coming to the in this region. Okay, delta phase and liquid. So which reason, which reaction it could be? One liquid converting into the one liquid plus one phase, monotonic reaction. Okay. Similarly, eutectoid reaction. So here, if you see here, one phase is one solid phase is converting into the two different solid phases. Okay, alpha phase and gamma phase. That is called as a one solid phase is converting into the two different kind of solid phases. Okay, eutectoid reaction. Okay, so up to this gamma region, we can so that's why it is called as a eutectoid reaction. I think it's got. Uh, okay, I think I cannot to create a new link now. So, however, I will continue my lecture and I will upload this in YouTube, and I will say you can access that link so that you can refer that one. So, I will continue my presentation, and you can access that one in further. So, here you can see. So that's why it is here gamma phase converting into the two one phase, one solid phase converting into the two different solid phases. Okay, that's why it is called as a eutectoid reaction. Here, when what is the meaning of eutectic reaction? One liquid converting into the two solid phases. Okay, here you can see here one liquid converting into the gamma and Fe3C phase. Okay, so that's why it is called as a eutectic uh, reaction place. So steels we can consider up to the 2%, and above that it will be considered as a cast iron. Okay, let's try to solve some of the problems which we have till now discussed. Okay, first is that welding is best defined as a option joining of the materials by using the mechanical fastening. Okay, second is the joining of the metals by melting without pressure. Third, permanent joining of the metals by with or without pressure, with using or without using pressure. D, temporary joining of the metal using adhesive. So what could be this one is? So as we have discussed previously, so welding is comes under the permanent joining case. Okay, so if it is the temporary joining, we cannot consider it as a so option A, joining of the metals by using mechanical fastening. It is a temporary joint, so it will not consider as a welding process. Okay, second, joining of the metals by melting without pressure. Okay, so welding we can join either using pressure either without using pressure, but there is no condition like without using pressure, so that we cannot I mean it is partially correct but not totally. Okay, third is that not to properly defines the what is mean by welding, because with the pressure also we can join like solid state welding, as we discussed, diffusion welding, roll welding, forge welding, explosive welding, those are all comes under this process. Okay, next is the permanent joining of the materials by with or without pressure. Yeah, so here it is mentioned with or without. Okay, Here it is only mentioned the without. So that means pressure cannot be used. But in some cases we are using pressure also. So this one is the not the right one. Okay. So here with or without. So it is the most satisfying one. So let's see the final one. The temporary joining of the metals under the adhesives. Okay, temporary joining is never considered under the considered as a welding process. So answer will be the C. Okay, answer is the C. So next, uh, welding of the following is not a fusion welding process. Okay, following processes, among the following, which one is the not a fusion welding process? First, what do you mean by fusion welding? Okay, fusion welding where we use the heat to join the two materials. Okay, so in which process we will use heat? So options what are there? One is the gas welding. So in gas welding we use a chemical reaction to generate the heat. That heat we will use to join the material. So it is definitely a fusion welding process. Okay, so next, arc welding. Arc welding also we use the electric potential between the two power supply portions like electrode and workpiece. Um, so that will generate the arc. Arc will generate the heat. So definitely we are using heat. So arc welding also not the one. And resistance welding. So resistance spot welding, if you see the because of the material's resistance property, heat will generate. That heat we will use to join the welding process. So if there is the heat is there, and it will melts the material, means it will becomes under the fusion welding. Okay, in forge welding there will be no heat because we will heat the two materials and make it join by cold working process. So answer will be the forge welding. Okay, next, in welding metallurgy, the term coalescence refers to. Okay, first is the cooling of the metal, molten metal, that is, and solidification of the weld metal, bonding of the metals by heat and or pressure, and grain refinement in the base metal. It will be the bonding of the metals by heat and or pressure. Okay, that is nothing but the welding definition. Okay, the heat affected zone is defined as a. Okay, so how we can define the heat affected zone? Yes, previously we have seen, um, so if we see here, so here is the base material, and here is the weld bead, and weld bead having the temperatures above the melting point of the material, base material, so that here in weld bead, during the welding process, it will be the in molten state. Okay, but in parent material, the temperature below the recrystallization temperature, so that microstructure will not be changed. Okay, but in the case of the here molten region and the below recrystallization temperature, the temperature will be above recrystallization temperature of the this metal. So because of this reason, the recrystallization temperature, it is above the recrystallization temperature, the material will melt it will microstructurally, I mean, grains will grow and forms as a coarser grains. Okay. So we can see the options. A molten weld metal, because that is not the right one, because molten weld metal is the weld bead region. So unaffected base metal, this is also not, because unaffected base metal, there is no crystal structure is taking place. So this is also not. Okay. So region adjacent to the welding that experiences the thermal cycles. Okay, just adjacent to the welding, that is their temperature is above the recrystallization temperature. So it is called as a heat affected zone. So it is the right answer. Finally, final one is that electrode coating region. Definitely electrode do not comes under the heat affected zone. So that is not, that is we call it as a flux. Okay. So these are the answers. Next, coming to the next set of questions. Which factor primarily controls the microstructure of the weld? Okay. Which factor primarily controls the microstructure of the weld? First is the color of the electrode. Definitely not. Because okay. Next, heat input and cooling rate. Yes, because heat input, amount of the heat input gives defines the amount of the weld zone is there. If the heat input is more, the weld zone area will be increases. Okay. And cooling rate also very crucial, because the cooling rate affects the what kind of microstructure forms in a given weld bead. Okay. If the cooling rate is too high, it will form as a columnar grains. If it is the cooling rate is slow, it may form equiatomic grains or like that. Okay. Next, ambient temperature only. No, that is not that much significant factor when coming to the microstructure of the weld. Okay. And welding position. No, because what are the welding position we are considering, the definitely the metal will melt. Once it melt means how it is cooling and what is the amount of the molten region, the area volume of the molten region, that only affects. So answer will be the B. Okay. Next question. Which zone is the weld zone under melted solidification? Okay. Okay. So which metal? So as we discussed previously, oh, which zone is here? We can see here. So it is the parent material, heat affected zone, weld zone. So here only weld zone is in the molten state, so that it will form as a weld bead. So heat affected zone, it will never it reaches to the molten region. Parent material, it will be stay in the same microstructure as a previous one. So the answer will be what is the options I have given? One is the base material, which zone undergoes the melting and solidification. So definitely base material is not. And if a heat affected zone, heat affected zone, it will reaches above recrystallization temperature, but it will not get melted. Okay. Next is the welded metal. So welded metal region, the region where the fusion is taking place there, and parent material nothing but a base material. So it will be the welded metal. Answer will be the welded metal. Next question. Heat input in welding is mainly depending on, okay, what electrode diameter only? No, definitely not, because heat input b voltage, current, and traveling speed. Yes, because once the voltage and current increases, the power supply increases. If the traveling speed here, voltage should be high, current should be high, and traveling speed should be low. If the traveling speed increases, the power density will be reduces. Okay, and so next type of the base metal. Base metal type of the base metal only tells the what is the melting point, but not about the amount of the heat input. Okay, atmospheric pressure, no, atmospheric pressure also will not affect. So answer will be the voltage, current, and travel speed. Which of the following welding process uses electric energy as a heat source? Okay, so options: oxyacetylene welding. Oxyacetylene welding is a gas welding. Okay, so gas welding is done by um, chemical reaction process. Okay, next is the arc welding. Arc welding uses the electric energy, so it will be the arc welding. In case of thermite welding, thermite welding also uses the chemical reactions to generate the heat, exothermic chemical reaction. Okay, here fuel will burn, that will generate the heat. And for seven D option is the friction welding. In friction welding, because of the friction force, heat friction between the two contact surfaces, heat will generate. So option will be the arc welding. Here we use the electric arc as a heat source, so that's why it is called as a arc welding. Okay, these are the answers. Okay, next coming to the next set of next questions. Metallurgy of the welding process is important because it helps in understanding why metallurgy is important. Is the so welded appearance? No, because we want to see the how the microstructure is affecting. Next, electric characteristic of the melting machines? No. And see microstructure changes and properties of the weld. This is the um, crucial aspect to so that the amount the strength of the joint is depend. And D is the cost of the welding. So answer will be the C. Rapid cooling during the welding generally results to, okay, so rapid cooling means which kind of coarser grains will only appear when the cooling rate is much slower. Okay, because there is enough time to grow grains to grow. Okay, increase in ductility. Coarser grains generally gives the higher ductility because So here there is no coarser grains. So uh, in rapid cooling, I don't think so. This is the not the right one. Formation of harder microstructure, yes, because rapid cooling generates the smaller, finer grains. The finer grains generally increases it uh, harder hardness of the material. Okay, and no change in the properties. No, definitely there will be a change in the properties when the microstructure is changes. Okay, so answer will be the C. Okay. So next we will try to do some metallurgical, some numericals. Okay. So this is the question: a binary alloy containing the 40 percentage of the B phase and uh, is at a temperature where it lies in the liquid plus solid region. Okay. At the temperature, the composition at the end of the tie lines are liquid at 60 percentage of the weight, where 8 percentage at B, so, and solid 20 percentage of the B. Okay, what is the percentage of the liquid phase in alloy? Take a few time and try to do it. If not, I will explain it. So answer will be the, by using the lever rule we can find out it. The fractional how we can find out is that here LO is the fraction of the liquid 40 minus 20 by 40. 60 is the where it is touching the liquidus line, and 20 is the where it is touching the solidus line, 40 is the where we want to know. So so it is the formula CO minus C alpha by CL minus alpha nothing but CS. Okay, CS by CL minus CS. Okay, that will give the 0.5, that is the 50 percentage. Answer is the C. Okay. In the similar previous question, what is the solid phase percentage? So how we can call find out is that, so here instead of LO minus CO minus CL, here we CL minus CO by CL minus CS. So that will gives the fraction of the solid percentage. Okay, only difference is the formula is that here we get the CO minus CS by CL minus CS, but here CL minus. Okay. So this is the next question. An alloy composition of 30% weight percentage B is in the alpha plus beta region. Okay. At a given temperature, a tie line intersects alpha at a 10 percentage of the B and beta phase at the 70 percentage of the B. What is the fraction of the beta phase? Answers. So answer will be the fraction of the beta phase. We can find out by, we know that the composition of the beta phase and the alpha phase, and here is the answer. Next is a 2 kg alloy composition. 50 percentage of the B is in the alpha plus liquid plus alpha region. At a given temperature, liquid 70 percentage of the weight, 70 weight percentage of the B, and solid alpha 30 weight percentage of the B. What is the mass of the liquid phase? So answer will be the similar to the previous formula, CO minus Cl by Cl minus Cs. Okay, that gives the fraction of the liquid. Okay, the fraction of the liquid is 0.5. So the total amount of the quantity is the 2 kg. So that we into multiply, that will be the gives the 1 kg. Okay, this is the final question for today. So a null is in the liquid plus solid region of the phase diagram. Which of the following is the true? The overall composition changes along the tie line. The phase composition are given by the end of the tie line. The amount of the each phase is given by the phase diagram directly. The lines are vertical lines on the phase diagram. So answer will be the tie line and ends gives the composition of the each phases. Lever rule gives the amount, not the diagram directly. The lines, tie line are horizontal, not vertical, and overall composition remain fixed.